Okay. So the idea is we want to compute homology spaces of Mobius strip. Now, Mobius strip, the way you make it is you take filled-in square and you glue this side to this side, but in the opposite orientation. So that every point here gets glued to a point down here. So in particular, this corner gets glued to that corner, this corner gets glued to that corner. So the way we want to do this as a simplicial complex, so the point is to using simplicial homology. So in order to do that, we need a simplicial complex. This is sort of the first pass of what you would want to lay out your vertices. And the point is you want to actually fill in each of these as well, so that it looks exactly like this diagram here. That's the goal. So every place that we filled in here, it's got to be filled in over here. And in particular, if I were to sort of ignore the boundary, the fact that this one got glued over to here, this two got glued over to there, this edge got glued to here, if I were to ignore that portion of the diagram, then I should just be left with something that looks very much like a rectangle. Now the problem with this particular way that I've written it out, this is sort of a natural way to subdivide it. This is not a simplicial complex because it doesn't have any triangles. So the trick is that what we want to do is we want to split it into triangles. Now the problem with this one though, is that if you look at the triangles, they're only identified by their vertices. So for instance, I have a 1, 2, 3. That's this triangle. Unfortunately, this 1, 2, 3 is already 1, 2, 3 right here. So this triangle and this triangle, they're the same thing.
Why are they the same?
Because they're, the only way I can, in a simplicial complex, the only way I can tell what's what is by looking at its vertices.
So
They have the same set of vertices and they are the same thing.
So are all four triangles?
Yeah. So this is a 1, 2, 3. This is a 1, 2, 3. And that was exactly my next point is, hey look, this one is 1, 2, 3 also. So this thing is glued to there. That's bad. This is glued to there. Also bad. So you don't want that. And the way to do that is to start adding some extra vertices. I'm going to erase all of this here and fill it in. So I added a 3 in the middle. I'll keep that 3 there. But now what I'm going to do is I'm going to put in here a points 4 and 5 and subdivide these. Now what did this do for me? Now this top one and this bottom one are not the same anymore. See, because these two top triangles both include 4. Both of these do not include 4. In particular, they include 5. This top does not include 5. So now these top two triangles and these bottom two triangles are protected. They're definitely different. Still have the problem that 1, 2, 3 over here and 1, 2, 3 over here. So you need to add some more vertices in here to take them apart as well. So really your goal in the homework is to figure out a configuration of how to subdivide this into vertices and edges and whatnot, so that only the things get glued together that you want to have glued together, and nothing else. Yeah?
How do you make one of the triangles into a matrix?
Okay, so remember, we're using simplicial homology. So we're going to build the simplicial chain complex. So what you end up doing, let's say I finished. Let's say I finished at this point.
We can do this. We've done this before.
Yeah, we've done that before, right. So you list all the various triangles that you've got. Those are going to be forming the basis of your second degree chain space. List all the edges, that will be the first degree chain space. All the vertices, that's the 0th, etc. Okay? So you do that for the Mobius strip. You do that for the Klein bottle. In order to make the Klein bottle, we take this edge and we glue it to there. In order to make it into torus, we turn this guy around. The torus is what happens when you play Pac-Man. If you're in the board over here and you go off the top of the board, you come in from the bottom. You go off from the side, you come in from the other side. In exactly the same spot that you came from. So that's what the homework amounts to, basically. Is really the main point of the homework is coming up with these simplicial complex structures.
What are these diagrams called?
These particular kinds of diagrams?
Yeah.
These diagrams, actually I'm not really sure if there's a good name for them, but they're basically, they're specifying a quotient space. We call them gluing diagrams or attachment. They're not quite attachment diagrams, but they're essentially gluing diagrams, telling you how to glue together the space. But from a precise standpoint, they're about forming a quotient space. Now, the connection between this kind of diagram and then a simplicial complex, though, is something that's actually kind of important from a theoretical perspective. We've been dealing with these guys. But at some level, this kind of space is more natural. If you will, draw a line in the sand. This is really about combinatorics, counting. And this is really topology. As in continuous maps, topological spaces, and other such things. This is really just enumerating stuff, telling you which of various groups I'm going to count. I'm going to count this many edges, count this many faces, count this many vertices, etc. And really, topology is about open sets or neighborhoods. There are no open sets that I've specified here. Of course, I can give this a topology, as in I can write down a collection of sets of vertices and edges and whatnot. And that collection satisfies the axioms of a topology, making them open sets. I can certainly do that. But I haven't done that explicitly. Yeah?
So is the edge on the left and right sides, if you were, no, on the abstract, if you were to, I mean, I know you have to subdivide it still, but
Yep.
for the arrows, do those determine which comes first in the face?
That's right.
Okay, so it's 2, 1, 1, 2, or whatever you, okay. And then that factors into the
Right, and actually, once you're done subdividing, if you've subdivided it enough, then actually the directionality turns out not to matter very much. That you can pick a backwards, if you will, counting of which one comes first, and just do everything in lexicographic ordering, as I've suggested in the past. You just use dictionary order and you're fine. If you don't want to use dictionary order, then you move out of combinatorics and into topology. And there you must stay. And if you look in Hatcher's book, for instance, he talks a lot about delta complexes rather than simplicial complexes. Delta complexes are topological. They're topology in nature in that they really expect a specification of open sets to disambiguate things. Whereas when we deal with simplicial complexes, we don't need that. Now, what today's lecture is about is making that connection between topology and combinatorics. And in particular, what I want to talk about is a way to use purely the topology to cook up, and in a very, very ambitious way, to cook up a chain complex. Start with a topological space, cook up a chain complex. It turns out that that chain complex will give you the same answer if you started with a certain topological space associated with a simplicial complex. So let me put all that together and lay out what that is. So, actually officially titled this lecture allows you to talk about homology associated to a topological space J. So, thus far, we have simplicial homology associated to abstract simplicial complexes. That's what we have. Simplicial homology associated to an abstract simplicial complex. This is linear algebra. This is combinatorics. And when people discovered singular homology in the early 1900s, a little bit of folk history, they did not exactly realize that they were doing topology. They thought they were doing linear algebra and combinatorics. And in fact, there's some papers even going up into the 70s where people were talking about associating homologies to certain kinds of combinatorial objects. And so it was an active and reasonable way to think about the problem. Certain combinatorial problems have certain linear algebraic formulations. The realization was that if you're working with abstract simplicial complexes, which are a particular kind of combinatorial structure, then you're really doing something topological. Now, what does that mean? Well, what I'm going to define now future tense, we will have singular homology associated to topological spaces. And again, singular homology is going to be found in linear algebra, or homological algebra. And topological spaces is, of course, topology. Now, if you haven't studied topology directly, or topologies or topological spaces directly, that's not a major impediment. I'll give you a little bit of an axiomatic way to look at this, a little bit of a review on what a topological space is. But I don't think, in order to get the main idea, it's essential. Now, these two stories look very similar. In fact, they are functors. I've got a category of combinatorial things that turns it into linear algebra. There's some causation, if you will. This is the way the information flows. I take my abstract simplicial complex, I turn it into linear algebra. If you were to give me a chain complex, just some random chain complex, you might not be able to give me back an abstract simplicial complex that gave rise to that chain complex. But every abstract simplicial complex you can turn into a chain complex. Now, similarly, what we're going to do is we're going to build something like this. It's going to take my topological space and turn it into a chain complex.
Dr. Robertson, for the first example, is the chain complex the functor?
The process of making the chain complex is the functor. In fact, what the functor is it takes two things. It takes the abstract simplicial complex, turns it into a chain complex. It's the act of doing it. And it's also the act of saying, if I have a simplicial map from one space to the other, that gives an induced map between homology spaces. So it's the act of transformation, which is why I've used it to label the arrow. Now, similarly, I'm going to take the act of transforming a topological space into singular homology. And again, that is going to be another functor. Now, the question is, do these things look very similar. Well, first glance, they're going to look wildly, wildly different. This one here is, you can write down the matrices. This one, you will not be able to write down the matrices. In no small part, because the spaces in the chain complex will be infinite dimensional. They will be uncountable dimensional function spaces. Bit hard to write those down as matrices. If you're a physicist, no problem, they do that. I'm not a physicist. In fact, this is one of the interesting interpretations of quantum mechanics, was to think of it in this kind of context. Now, on the other side of things, so those look far more different than they could ever be. Now, on this side of things, again, if I have a combinatorial object, this abstract simplicial complex, you know, I can actually make a topology from it. I can make a topology, in fact, in several different ways. I can take a look at this Alexandrov topology that I mentioned very, very briefly earlier on in the course, where I take a look at all this, all the simplices of larger dimension that are adjacent to a simplex, that turns my combinatorial thing into a topological thing. There's another way I can do it too, which is called a geometric realization. And, as one might hope, if I take simplicial maps, they should turn into continuous maps here. And indeed, as a result, it will be another functor. This goes under the name of geometric realization. It's a functor. And now, the surprising thing here. Now, it's not so surprising from the way I'm drawing the diagram, but this really feels like I want to fill in right here. Does this exist? Does this kind of functor exist? This is going to be a functor from chain complexes to chain complexes. Take a chain complex, give me a new chain complex. It doesn't actually work out on chain complexes exactly as cleanly as one would hope, but surprisingly, it does on the level of homology. This, in fact, which is to say, if I start out with an abstract simplicial complex, compute its simplicial homology, and then think about it in terms of singular homology. Think about it and take a look at the homology that I get there. Or take that simplicial complex, geometrically realize it into a topological space, and then compute what I'm going to show you, this singular homology, then in fact, they have the same homology. Now, it's not possible to go from a general topological space to a reasonable abstract simplicial complex. You can't exactly reverse this process. So that's why I've kind of drawn it down here, but it is an isomorphism on homology. It is not an isomorphism on chain complexes. And that makes this particular theoretical machine very, very subtle. Very, very subtle in that regard. So it preserves homology, these quotients, but it doesn't preserve the actual chain complexes themselves. It does preserve maps between homology. So it really is a functor in some fashion. It is a functor, but it's not a functor on the chain complexes. It's a functor in a different category.
When you say geometric realization functor,
Yeah.
you mean drawing a picture?
That's basically that, formalizing that process. Yes, exactly. So it is literally formalizing the process of drawing the picture of the simplicial complex. In the process of, say, taking this combinatorial specification and drawing it in a very precise manner. Which is to say, I'm going to draw out the edges as a set in Rn. I'm going to draw out each of these faces as subsets of Rn. Now this is not at all easy. In fact, this is actually fairly subtle to specify this. I would say it's actually kind of a pain to write that down. Because it's very easy for you to say, I want to draw a line from here to here, from this vertex to that vertex. In 2 dimensions, no problem. What about arbitrary dimensions? Well, I'm going to want to say that this face here really has to glue to that face there, and it gets really very subtle. So it's not so clean. But basically, yeah, you can think of it as geometric realization amounts to drawing.
And would it be correct to interpret this diagram as saying that singular homology has the least information of all these categories?
Singular homology, in some sense, actually, what's really very interesting about this, I wouldn't say it has the least information per se. In particular, because you end up with an isomorphism on the homology.
So then you can go back.
You can go, so in fact, if I started with an abstract simplicial complex, computed its geometric realization, I drew a picture of it, computed the singular homology of that, whatever information that I've got there is actually exactly all of the information I would have gotten if I had just computed its simplicial homology from the outset, because of this isomorphism. The functor naturally goes this way, but it is an isomorphism.
So then should the arrow be
double-ended?
Yeah.
You know, this is what I'm hesitant about. This is a very subtle topic. Yeah.
So if it's an isomorphism on the homology, are those two homologies of the same dimension?
Yes. Even though the chain complexes here are uncountably infinite dimensional, the homology is actually, if you started out with, say, a finite simplicial complex, the homologies could be finite dimensional.
Sure, because like you could have two matrices of infinite rank, but their difference could be finite.
Yes, that's essentially the point.
Okay.
Their quotient, yeah, essentially, yeah.
Yeah.
Okay, so that's kind of the goal. This is a fairly subtle theorem. This occupies a rather substantial portion of Hatcher's chapter on homology. Someone wanted to talk a little bit about that as a project. That would be a good final presentation, actually. And that's kind of why I'm going to step back from that. And I'm going to focus today on defining singular homology. Basically just to show you that you can get chain complex in a topological way. Okay, so let's do that. Okay. I'm going to start with a topological space, and it's worth noting what a topological space is. And when I say functors with topological spaces, I mean something. I will remind myself more than anything else, topology is not a prerequisite for this course, so I'm not going to rely on it heavily, but I'm also going to just basically look at it axiomatically at this point. So, definition. For a set X, so any old set, a topology, T is a collection of subsets of X thus far, I could have been on my way to define an abstract simplicial complex. For a set of vertices, an abstract simplicial complex is a collection of subsets of those vertices. Word for word the same thus far, except for the word topology. But now I'm going to deviate from that, such that, first off, the empty set is in my collection. The whole set is in my collection, and here I deviate from abstract simplicial complex. And this collection is closed under intersection. So it's closed under intersection. I can extend this to any finite intersection. So take a finite number of sets, intersect them all, and that will still be in my collection. And I'm allowed to take any unions whatsoever I like. So if script U is some set, I'll call it U alpha, some collection of elements of T? Well, that's a collection of subsets of X, so it is reasonable to speak of their union, the entire collection's union, and that entire collection. Now, it's easy to forget which of these axioms go which ways. The picture here if I have a bunch of open sets and I'm trying to shrink them down to a point, take a bunch of open sets like so, try to take them to a point, take the intersection of all of them, this is not open. While if I were instead to take the union, that is. That's the mnemonic. And the point is that the elements of T are called the open sets for your topology. So this is an axiomatic recap of what a topology is. And this definition, I think, goes back to a mathematician by the name of Hausdorff. And the point of the matter is not so much that any given topology is interesting. I mean, any given topology might be interesting, and there are lots of different topologies I might put on a set. But what's really interesting about topologies is the fact that I can transform them from one to the other. And those are what are called continuous maps. Yeah.
Just quick question. That set that you've defined there, that you were taking the union and intersection of, that set could also be an ASC, is that correct?
Yes, indeed. Certainly could. Not the ASC I tend to have in mind, because that's an awful lot of vertices.
Yeah, yeah.
But yes, yes it could. In fact, anytime you have a pre-order, so any kind of ordering of various objects that I may not be able to compare every particular pair of objects, but I can say X is less than Y sometimes. And if X is less than Y, and it's not the case that Y is less than or equal to X, except in some special circumstances, that's called a pre-order. And the point is, every time I have a pre-order, I have a natural topology on it. It may not be the topology you're used to, because there's topology. And that gives rise to the kind of abstract simplicial complex you'd get here. Anyway.
Does 3 imply countable intersections?
Yes.
Let's call it,
Yeah. These are countable intersections. These are any arbitrary unions.
Okay.
Yep. All right. So the point of topological spaces is that it's a pair of these two things. So a topological space pair X comma T. That's a topological space. Okay, so now the important thing about topological spaces is their mappings. So definition, a continuous function and we write it like so. This is the notation. This is the notation. But really, f is just a function from x to y. It's just a function from x to y. Is such that, this is a different topology on, call this
S.
S, all right, S it is. All right, such that if U is in S, then F inverse of U is also T. Put another way, whenever I have a open set in the codomain, its pre-image is open in the domain. The inverse seems a little weird, but you get used to it, and part of the reason why it's there is to permit certain kinds of set axioms to play out nicely about intersections and unions, as you might suspect. So a little bit of set algebra comes out better when you've got that pre-image there. Okay, so that's a continuous function. And the point of the matter is that continuous functions, essentially, what they do is they map topologies to topologies. All of the open sets here are somehow represented over here.
So that's right, they preserve open sets.
They preserve open sets. Yeah, continuous functions preserve open sets. Now, this is the machinery we need in order to start building singular homology. Now, singular homology is really, really built off of the idea of simplicial homology, which is why it's not that surprising that they match up in the end. It's sort of a long, circuitous path, but the reason why they match up is because basically what you look at in singular homology is continuous images of a very particular kind of space. So continuous maps starting in a very particular kind of space. So this X is chosen to be something very particular. Okay, so let's make that happen. Let's talk about that particular kind of space. And what I'm most interested in singular homology is I'm most interested in continuous functions whose domain is basically topologies that you're familiar with. The range could be anything. We don't care so much about the range at all. So let's build up the domains that we're going to use. They're very particular spaces. There's subsets of Rn with the usual topology as you're used to. So it's singular homology. Built on what are called standard simplices. So, definition. The standard K simplex, and write it delta sub K, is the topology of the space. Is given by subset set of all points in Rk plus 1 such that, well, first of all of the coordinates are non-negative. And there's some is equal to 1. That's the set, and it's just got the usual topology in Rn, or Rk plus 1. Now, this is a very, very particular set of sets. So I've got a bunch of points in Rk plus 1, a bunch of loci of points, and I'm just going to use the usual topology that I would know and love and expect in Rk plus 1.
What is the usual topology?
The normal set of what you would think an open set is in Rk plus 1. So take, if you like, you take the usual Euclidean metric and take a look at that, all the balls that it generates. Those are going to be the base set for the open sets. But basically, this is why I said topology is not a prerequisite for this course, basically, is because this is the usual topology. It's what you'd expect from plain old calculus. Open sets are open sets. All right. So now, what do these things look like? Well, there's standard simplices. What does a standard simplex mean? Well, let's start out. Let's look at delta 0. What is this? This is the set of all points in R what? Set of all points, x0, in R1, such that x0 is positive, and
And to 1, so it's just...
x0 is equal to 1. Yeah, so this is a superfluous condition now, isn't it? This is just basically the point, x0 equals 1. So if I were to write this, there's R1, and that guy is delta 0 at 1. Okay, now what about delta 1? This is the set of points, x0, x1, in R2, such that both of them are positive, and they sum to 1. Oops. And a little bit of drawing, I think, should tell you what this is. It's in the first quadrant, and what does it look like? What shape?
Half a sphere, or a quarter of a sphere? Oh, sorry, it's a line.
It's a line, yes. No, don't overanalyze this guy. Yeah. So there it is. That line's it. Now, delta 2. It's in R3. I'm not going to write out the space specification. I'll just draw it pictorially. Here's x0, x1, x2. It's in the first octant. And what happens? Well, it is this plane bit. It's that little plane bit. Now, something kind of neat should show up here, is that the standard K simplex contains all the K minus 1 simplices and all the K minus 2 simplices all the way down the line. Here's the standard 1 simplex, and look, it's got a 0 simplex and another 0 simplex. The standard 0 simplex, where I'm imagining R1 as the x0 coordinate, as I've written here. But if I were to relabel the x0 coordinate as the x1 coordinate, there it is. They're both there. Now what about the standard 2 simplex? Well, it's got 3 standard 1 simplices depending on which pair of coordinates I'd like to use. If I'd like to use the x0, x1 coordinates, like I did here, to make this standard 1 simplex, hey, there it is, right here. That's the standard 1 simplex. So this is the standard 2 simplex, right here. The standard 1 simplex is right there. And the standard 0 simplex is also present. So, these standard simplices do kind of work a bit like simplices, because now I can start thinking about permutations of which coordinates I'm going to keep. If I project down instead of to the first 2, but to the, say, the first and the third, I get this copy of the standard 1 simplex. If I instead just consider the last 2, I get this one, etc. This is a simplex, an abstract simplex, but this is a geometric realization of that simplex. So the standard simplices are the geometric realizations of the various other simplices that are abstract. Now, in order to make the geometric realization functor, as I have written it, what you now need to do is take a whole pile of these, one for every K simplex, and start gluing them together. Build up a topological space that consists of, take this one, and another one like this, and another one like this, and another one like that, a whole bunch of them, and then say, all right, all of these points on here, they're the same as these points over here. All of these points over here are the same as there. Basically run beads of glue all over the whole thing and stick it together.
So these things are open sets?
No, actually the open sets are the open sets that are ambient in R K plus 1.
Right, okay, sorry.
So there are lots of open sets. Huge collection of them. This geometric realization functor takes an abstract simplicial complex, this combinatorial thing, and turns it into this huge thing with uncountably many open sets. Kind of awkward. Using the Alexandrov homology is a little slicker, and actually that's what Alexandrov meant to do when he wrote his paper in 1937 on this topology, was to show that you could do it in a lot slicker manner. But this way here is very visual and literally is drawing a picture, which is why I think it's a very nice way to think about it. You visually see this is what's going on. And it's also the link into what is singular homology. Okay, so these are the standard simplices. Now, these standard simplices basically have nothing to do with a typical topological space that I'd like to study. That's kind of bad, because I want to study topological space, I don't study these things. These things are kind of not very interesting. From a topological standpoint, in fact, all of these things can be squashed to a point. They're all contractible. That's decidedly uninteresting from a topological standpoint. The only thing they've got is dimension. So now what I'm going to do is I'm going to link it up to the space in question using a continuous map. Okay, so now we're going to introduce the study of a particular topological space. We're going to have to circle back and talk about standard simplices in just a little bit. But hold in your mind the idea that by projecting down to the various sets of coordinates, I can get all the other simplices in the boundary. Okay, so I'll pick a space to study. Call it YS. I'm interested in YS. This is a topological space. And I'd like to know something about this YS. So what I'm going to do is I'm going to start examining this space. And the way I'm going to examine it is probably the most primordial way that humans examine things, by poking at it. I'm going to poke at it with these various tools. I'm poke at it with points, poke at it with line segments, poke at it with higher dimensional things. And the way I'm going to poke at it is with continuous maps. So definition. A singular K-simplex in YS is a continuous map. Sigma going from the standard K-simplex into YS. You can think of it to a first approximation as being the image of this map, but it's not just the image, it also captures the whole mapping process. So in particular, there's some orientation that's in there too. So, for instance, if I'm studying R2, say the board, what I've drawn here are the images of various singular simplices. Here is the image of the singular 2 simplex. Here's a singular 1 simplex and a singular 0 simplex. There are images in the board, so there are these continuous maps. You can think of singular 1 simplices as being paths. Singular 0 simplices, what do? They take a point, single point, that single point equals 1. Take that single point, and they tell you where is it in the space. So, intuition. Singular 0 simplices specify points. One simplices specify paths. They have a definite start and end point and some continuous path in between. 2 simplices, well, they're not paths anymore. There's something kind of else. They're Well, they specify these filled in triangles. I don't know quite what they are, but
The plane?
yeah, I mean,
Subset of a plane?
well, kind of, but think about it this way. You know, if I had a singular 15 simplex and I mapped it into R2, it's going to look very much the same kind of thing. But how those points got there is rather different. So they specify something, yeah, that's kind of plane-like. But I hazard to call them planes. So, yeah, they specify something. The intuition is good here. Okay, so now we've got all these continuous maps. And here's the audacious thing that one does in singular homology. One looks at these set of functions. There's lots of these. If I have an uncountable number of points here, say Rn, I get a lot, uncountable number of singular simplices. Of dimension 0, dimension 1, and all the way up. Lots of singular simplices. Well, we do what mathematicians often do in such a bind when we say, let's take them all. Let's see what happens when I take them all. Let's see if anything breaks. And in fact, that's really the right idea. So the singular chain complex is going to be built up in the following way. I need to specify some chain spaces and some boundary maps, as you might suspect. I'll suppress the S for a moment and just say ck of y. This is the set of all linear combinations of singular k simplices. Now, immediately I'm going to get into trouble if I say this, because that is such a dastardly large space that this is bad. So to make it a little bit better, instead of all finite linear combinations, so most of the coefficients are 0. But basically, this is like the same kind of thing that I did when I made simplicial homology. Took the set of all linear combinations of k simplices. But now I've set singular. So these are a whole collection of functions. And I'm thinking that I can add them in some fashion, but like, really, can I add them? Well, not really, so I'm just going to kind of use the coefficients to keep track. This is a huge space. Absolutely massive space in most cases. In fact, if y is not finite, this space is not finite dimensional. That's kind of bad, I suppose, but it's what it is. This is the audacious proposition here that we're going to make, is that we're going to just say, let's just try this, see what happens. Now, any boundary maps? Boundary maps, what are they going to have to do? They're going to have to go from k to k minus 1. As before. And what am I going to have to do? I'm going to have to take a singular simplex, singular k simplex, and turn it into a linear combination of simplicial singular k minus 1 simplices. Oh gosh, I mean, this is this awful function space. How do I even do this? Well, the hint is the as before. And what I mean by that is, let me take a singular k simplex. What is that? It is a function that takes how many variables? This is in rk plus 1. It's a function that takes some points in rk plus 1. It tells you where to put them in y. This is going to be a collection of functions in rk. And all I need to do is tell you where to set them in y. And which coefficients go where. Okay, that doesn't seem quite so imposing. So let me try it. Let me start out with a singular simplex, k simplex. And let me tell you what's going to happen to that single singular case simplex. Now, I have to tell you by specifying a bunch of functions over here. So this better be a linear combination. Whatever this thing is, better be a linear combination of functions. Okay. Well, I basically only know one trick in this class. Something like this, and then I'm going to be like leaving stuff out. And the difficulty with this leaving stuff out part is that, well, what I want to do is I want to write something like this. And this is going to be wrong, but I'm going to write it down anyway. Really what I want to do is something like what we did when we had the simplicial boundary map, where I take my sign from the entry I get rid of. This is what I want to do. But there's a problem with this. What's the problem with this? Why can't I do this? Why can't I do this? Why is this not the right thing to write down? There's actually a type error here. Yeah?
Yeah, I'm not sure that, do we have a great definition of what it means to take the sum of a k-simplex and another k-simplex that happen to live in the same space, but we haven't defined a simplicial complex containing those points?
No, that's not a problem. What I'm doing is I'm saying formally, I'm going to make some algebra. And I'm just going to think about making a vector space on which these are naming the basis.
Okay.
So that's not so much the issue.
Okay.
The issue is with this formula itself. This formula is not legitimate. It is not, in particular, a legitimate map as I've written it here. What's wrong with this formula? It's a type error. Started out with a singular k-simplex. This is a function that takes rk plus 1. Takes points with k plus 1 coordinates into y. What I'm supposed to be giving you back, the output of this thing should be in k minus 1. It should take points in rk, tell you where they go in y. Why does this not do that?
Because the points don't go into y.
Yeah, why don't, well, no, actually points go into y just fine.
They don't go into c k minus 1 y.
You know, they don't go into c k minus 1 y. Why not? Well, here's the thing. It's one of these things where you got to look at it, and you got to look at it cross-eyed for a while until you really see, oh, that's why it's messed up. What's going on? Yeah.
Well, if you take like that vector right there of x0 through xk,
Yep.
that's going to be like so that is a convex vector, meaning all of the entries sum to 1, right?
Yeah.
So if we subtract one of those vectors from another one, there's no guarantee that the result is convex.
Yeah, and I'm not asking for that to happen. I'm not assuming this, that would be assuming that this is a linear function. I'm not asking for that. Not asking for that at all. But you're close. There's a problem with this specification right here. This is the problem. Well, ask yourself, what variables does this expression involve? What variables? A bunch of x's, right? Which subscripted x's does it involve? X.
0 through k, not I.
Yeah, for this particular term in my sum. Now, if I take a different term in my sum, which variables does it involve?
What did you say?
Okay, so you're right. If I take a look at this particular term, as I've written, it involves x0 through xk, not involving xi. That's good. That's k minus 1
So if
variables.
you take a different term, so we have 0 to xk minus xj.
Sure. So I get rid of xj. Now, what about the union of those? Because I'm using both of them in writing my linear combination.
Total still has all.
Yes, my total still has all of those variables.
So you're going into CK?
So I'm still in CK.
Yeah.
Oh.
I'm still in CK. So what I need to do, probably doesn't leave enough space here, is I need to do something to fix this formulation so that at each stage the only variables that are invoked are x0 up to xk minus 1. So in fact what I'm going to do is I'm going to look at the various possible projections that come out of this. And in each case, only invoke those variables up to k minus 1. So I go up to x0 up to xk minus 1, and take a bunch of different x0 up to k minus 1s, potentially, depending on the fact that I have different, that some of them might be different singular simplices. So that's a little weird, but that's in fact what we need to do. What we need to do is we potentially need to permute these entries. Here's the picture motivation of that, because this is a little hard to see now that the problems are here. Let's take a look at that singular standard, that standard 2 simplex again. Here's the standard 2 simplex. Here's the standard 2 simplex. Here's x0, here's x1, here's x2. Now, when I'm thinking about this standard 2 simplex, I'm thinking of it x0 first, then x1, then x2. That kind of orientation associated with it. What I'm doing with my orientation, in particular, is I'm looking at the various possible maps that I might have. Looking at the set of points that are getting mapped in here. So what I'm going to have to do now, the images of this map, are they a problem? No, the images are all in Y. Never left Y. The problem is with the domains. What I need to do is when I'm sitting here, and if I were to delete the last coordinate, the x0, the x1, that fills in this edge here. If I want the x1, x2, that fills in this edge. And this one here, of course, is sigma x0, x2. So what I need to do is I need to somehow pick out these different components. So in particular, what I need to do is I need to think about the various possible ways that I can light up the different faces of the standard k simplex, the various k minus 1 faces. The realization here is that there are a bunch of maps. There are a bunch of maps that look like this. I is already used, I'll call them capital I. So I, which go from the standard k minus 1 simplex into the standard k simplex. That's what these green spaces are going to do. I'm going to take the k minus 1 simplex, I can go 1 simplex here, map it into my k simplex, fill in that edge. I'm going to map from this k minus 1 simplex, say, here, onto this edge. And I've got a whole bunch of them. Up to k. Because these are exactly going to be the boundary faces. So now, in order to make this a legitimate formulation, what I need to be doing then, I'm going to write this down. This is in essence what this I map is doing. It's picking out the various k faces. Then if I go ahead in here and make this composition, now I'm fine. Because now this starts out, what's the domain? Delta k minus 1. What's the domain of this function? Delta k. Delta k minus 1 into delta k, that's a legitimate function. And then from delta k, where does this go? What is the range? Into y, just as we want. So this fixes the problem. So the observation is the various faces can be written out using these maps. What do these maps do? Well, they're actually not so hard to write down. Essentially, all you do is you have to fill in some points. In fact, actually, let me write it over there, so it's all in one spot. x0 up to x k minus 1. What is that? It is x0, and I fill in a 0 in the ith slot. And then keep going, and go up to k minus 1. Notice, if I started out and each of these numbers were non-negative, are each of these numbers non-negative? Started out with the numbers up top being non-negative, the numbers on the bottom, I just added 0, 0 is non-negative. Yeah, they stay non-negative. If these guys sum up to 1, do these guys sum up to 1? Yeah, they do. So that means that I'm right. This is in fact a function taking these points in this set to these points in this set. For instance, now let's take a look. Let's take a look at what happened. If I take the standard 1 simplex, which lives right down here, and fill in the last coordinate with a 0, I get this image here. If I fill in the second coordinate with a 0, I get this one, and I fill in the third coordinate with a 0, I get this one. So that, in fact, builds out the right thing. So rather than eliminating, as we did before, we're now shoving in a 0, and that finishes the process. This thing now is our boundary map. And by exactly the same computation we did before, this, in fact, is a chain complex. As in, if I compose boundary k and boundary k minus 1, I get 0. For exactly the same reason. Same algebraic trick. As in, that there's a bunch of permutations. If I have 2 zeros dropped in here, I do capital I sub I, and I could do a capital I sub j, or I do them in the opposite order. The zeros swap places, and I pick up an extra minus sign, everything cancels out. Same exact argument as before. It's literally go through and just change it as it needs to be changed. That gives you a chain complex. So what we've actually done now is we've taken an arbitrary topological space. We've assigned a chain complex to that topological space. It's massive, but well defined, and so we end up with a homology for it. And the surprising theorem, which, as I said, would be a nice little final presentation for someone, is that in fact you get the same thing as singular homology. Surprisingly, if you start out with a simplicial complex, you build out all these standard simplices, glue them together, you get the same homology as you would have if you just started. Yeah.
So what you're doing when you take this sigma compose I, is so what you the vector that you have in RK, you take that guy and each time you delete the ith.
No, each time what I do is I just insert a 0 and push everything else downstream. Here, this is a vector in RK.
Well, but once you've inserted that 0, you were already in RK minus 1.
I'm in RK here. 0, 1, 2, 3, 4, 5. I'll take that minus 1.
Okay.
Python, yes.
Yeah. Okay.
So I've just popped in a 0. Now this is RK plus 1. And now this guy is ready to take a vector in RK plus 1. Ready to go. So I started out with a vector in RK, and now I've turned it into something that I can feed into a function if it wants it. Okay. And the point of the matter is this then really, this particular machine cements the connection between topology and homology. All right, and that's all I had for today. Would you grab the camera, please?
Yes.
Dr. Robertson, are you going to go to the math club meeting? We're having